Okay, so we've discussed various aspects of quantum error correction. We've discussed what I think are the key ingredients that you need to know and understand what a quantum error correcting protocol is. What is a code? How do you encode? How do you detect errors? How do you correct, etc. Right? What I'm going to do for the next maybe 2-3 lectures is to put whatever we've learned so far about quantum error correction and quantum error correcting codes into a nice mathematical framework called the stabilizer formalism, right? And with this, we'll more or less conclude our discussion on quantum error correction, right? And this next 2-3 lectures will also obviously conclude our mid-sem syllabus, right? And post mid-sem, we will change track and we will start discussing aspects of quantum information theory, right? Once we understand or we learn a bit at least about the stabilizer formalism, in my opinion, you are now well equipped to actually go and start reading papers, even papers that appear now on the subject. Okay. So this is a kind of culmination of whatever we've been discussing so far. It puts things in a bit more abstract framework, but at the same time, this is also, as you will realize, a more convenient way to talk about quantum error correcting codes. Okay. Some of you have already written to me about the final term paper and the presentation and stuff. We'll get to that once we finish the mid-sem. Okay. So next week, I'll sort of wrap up this whole discussion on quantum error correction, and then you have the mid-sem, not this Saturday, but the Saturday after. And post that, I will upload a set of papers from my site on Moodle, and then you can all decide if you have other papers that you want to talk about, that you're already reading, that you want to write about, etc. Please feel free to share it with me over email. Okay. All right. So what have we done so far? We know what the key ingredients of a quantum error correcting protocol are. You have the noise channel N, you have a code, which is some subspace of a larger Hilbert space, and this is identified by the projector P onto the code space. And then you have a recovery operation, which we can break down into syndrome plus unitary usually, right? Okay, so what about code parameters? Just give me a second. Sorry, let me just pause. Okay, sorry about that. I hope you can still hear me, and I hope, yeah, okay. Okay, so this recovery is what we discussed via a syndrome, which is a measurement, syndrome detection or syndrome measurement, followed by a unitary operation. And we've discussed all of this in some detail using a lot of algebraic analysis in the last couple of lectures in the form of the quantum error correction conditions and all that, right? So now, what we discussed in the last part of yesterday's lecture was to talk about what I call code parameters, right? So this is what describes a protocol, right? That there's a code space and there's a recovery, and you associate some set of errors of some noise channel which this code and recovery can correct for. In more general terms, how would you describe a quantum code, right? So this often in the literature goes by the name of code parameters, and one often writes like this, and this takes off from the kind of terminology that is used in classical error correction actually. So we often talk about an NKD quantum code, right? So the three parameters that we associate with a quantum code. So this I already discussed yesterday when we were doing the Hamming bound to some extent. So first K is the number of qubits that we would like to protect, right? So number of qubits that are protected rather that are to be protected, let's say. Or in other words, is the number of qubits that are encoded, right? The N describes the dimension of the space into which you are encoding. So this is the number of qubits into which k qubits are encoded. Okay. And finally, the D is what is called the distance of a code. Okay. And this we'll discuss a little bit today since I've not mentioned this so far. It is called the distance of the code. And this has to do with the number of qubits, rather, let me say, this tells us that the code can correct up to errors on how many qubits, right? So maybe I should say the number of qubit errors that the code can correct for. Okay, I'll explain this a little bit. So first of all, note that all of this is being said with reference to qubits, right? So these three parameters are being described with reference to qubit systems only, right? So these are all code parameters for qubit systems. If one is talking about qubits or higher dimensional systems, then you usually put a little subscript here where Q denotes the dimension of the single quantum system that you're talking about, right? So this would be for, so let me say, yeah, so this would be for Q dimensional quantum systems. Which means that the starting point is a CQ space, but of course there are K of them. So this will be CQ tensor K, etc. So first, just want to note that this formalism, of course, nowhere in the error correction conditions and so on did we restrict ourselves to dimensions, to just qubits, right? So you can, of course, talk about higher dimensional systems, and all these the same set of code parameters can be used to talk about higher dimensional systems as well, right? That is the first thing that I want to mention. So now going back to qubits, right? So this is just an aside. So let's go back to qubits. So let's talk about an NKD quantum code. So you're starting with qubits. So of course, a single qubit is C2, right? The associated Hilbert space is just C2. Now we're talking about starting with K qubits. So the associated Hilbert space is going to be C2 tensor K, right? You're starting with, so far the codes we have, all examples that we have are all single qubit codes only, right? So when I talk about a 3 qubit code, I start with just C2. But more generally, you can think about starting with K qubits. You can start by saying, I don't want to just protect a single qubit worth of information. I want to talk about K qubits worth of information, and I want to see how to encode K qubits, right? So this has a dimensionality of 2 to the K, right? Just like how a single qubit has dimension just 2, the K qubit system has dimensionality 2 to the K. If it were a K qubit system like here, if the single quantum system dimension is not 2 but Q, then you would have a Q to the K dimension system, right? Anyway, that's again the aside that I was talking about. So your starting point is this. So now you want to encode this into n qubits. So of course you will want n will be to be greater than k, right? That's when the whole encoding idea even makes sense. And so this will be associated with the C2 tensor n system, and this will have dimensionality 2 to the n, right? So now what is the code space dimension? So the 2 to the n is the dimension of the full encoded space, right? So this is the dimension of the complete encoded space. What is the code space dimension? This is the code space dimension, right? So this is the code space dimension because that is the information that you want to protect, right? So you are talking about encoding. The larger space is of dimension 2 to the n, and within that you have a 2 to the k dimension code space, right? Into which you're going to encode this k qubits worth of information. I hope the idea is clear. So far, we have only been talking about the case where the code space is of dimension 2 because we've only been encoding single qubits. More generally, you can talk about k qubits. Encoding k qubits will mean that you're looking for subspaces of dimension 2 to the k inside a 2 to the n dimension Hilbert space. Okay? So the dimension of the larger Hilbert space is 2 to the n. The dimension of the code space is 2 to the k. Now, where does the error correction property come in? What are the set of errors that can be corrected by this n comma k code, right? So in talking about this, the second point to note, the first was, of course, that this is all with reference to qubits. The second point to note is we are now talking about discretizing the errors in terms of the Paulis. This is what we discussed yesterday, that because the error correction conditions are linear, you can simply correct for identity x, y, and z if you're talking about qubits. And by virtue of linearity and the fact that identity x, y, and z form a basis for any single qubit operator, we can now, therefore, we would have corrected for any arbitrary single qubit error. So discretize the errors in terms of the Pauli errors, the so-called Pauli errors, which is basically identity x, y, and z, right? So when I'm talking about errors on how many qubits, it's understood that one is actually talking about arbitrary single qubit errors. One is not talking about a particular noise model. One is actually talking about, so this whole NKD code that one is talking about is what is called a general purpose quantum error correction code, because it's going to correct for arbitrary single qubit errors via this discretization. Okay. So the third parameter, which is the distance, basically has to capture this aspect, right? It has to tell us that the code can correct for arbitrary single qubit errors on how many qubits? Well, it's not, D itself does not talk about the number of qubits on which, up to which this can correct errors. It's actually a related parameter, which is called T, which is D minus 1 by 2. There's a reason why we are defining it like this, but basically this is what the distance tells us. So I should say up to. So the distance parameter tells us that the code can correct for arbitrary single qubit errors on up to T qubits, which means, of course, it can correct for errors on fewer than T qubits as well, where T is related to D as D minus 1 by 2. Okay. So an earlier version of this would be to talk about directly NKT codes, where T will tell you that the code can correct for errors on any subset of T or fewer qubits, right? But the right way to talk about distance, as it will turn out because of this whole stabilizer idea that we'll discuss now, is actually as in terms of, not directly in terms of T, but in terms of D, where D is 2T plus 1. Okay. So let me write this in a different way as well. So the NKD code can correct for errors on any subset T, obviously T is less than N, right? On any subset T or fewer qubits. So that's what the distance parameter talks about. It tells you how many errors the code can correct for, right? So let's now look at some of the codes that we already know and try to write them in this way, okay? So, for example, what about the Shor code? What are the code parameters? What is N? What is K? And what is D? Can anyone tell me?
N is 3, K is 1, and D is 1.
K is 1, that's right. I'm talking about the Shor code. So N is?
N, so we used to, oh, okay, so it is 9.
So for the Shor code, remember N is 9. Remember that the code words are, you take the repetition code and you have to concatenate it, right? These are the code words, right?
Yes.
Okay, so this is correct. Good. So you have encoded K qubits into 9 qubits, right? So K is 1, N is 9. What is D? So this can correct for arbitrary single qubit errors, right? But
So it
remember,
should be 3.
exactly, good. Yeah, so D is actually 2T plus 1 and T in this case is 1. And so D is actually 3. So the Shor code is what will be called a 913 quantum code. Okay. One can also try to do this exercise, let's say just for the 3 qubit repetition code. But it actually does not make sense to talk about a general set of code parameters for this. Why is that? What is different between the 3 qubit and the 9 qubit?
Yeah, it cannot correct any arbitrary error. It only can correct up either bit flip or phase flip.
Exactly. So depending on, good. So depending on whether you're talking about the bit flip code or the phase flip code, and they're both related to each other as we know, this is not a general purpose error correcting code. Right? But within that limited set of errors, if you assume that your world has only X type error or your world has only Z type error, then you can think of this as a 313 code, right? With the caveat that you only have X error or Z error. And what does this Hamming bound that we discussed yesterday tell us? So remember yesterday we discussed something called the quantum Hamming bound. after we discussed the error correction condition, we discussed this quantum Hamming bound, which was basically a kind of packing argument, right? The question was, well, you have this big encoded space, which has dimension 2 to the n, and inside that you have your code space, which has dimension 2 to the k, right? And now under the action of errors, this code space is going to get mapped to different subspaces in this, right? And now if you want to be able to detect and correct for all possible errors on up to t qubits, right? Then how many such distinct code spaces should you pack inside this 2 to the n dimensional space, right? And it turned out, we worked this out, you assume that you have one of 3 Pauli errors and you sum over all possible Pauli errors up to t qubits, etc., right? And then we showed this Hamming bound, which was so the Hamming bound actually said that if you sum over, so there are n comma j ways of choosing locations for the errors. There are 3 to the j possible errors on j qubits, and then you sum over all j from 0 to t. This times 2 to the k should be smaller than or equal to 2 to the n, right? So what I've summed over here is the number of all possible Pauli errors on up to t qubits, right? And each such subspace corresponds to one such error. And each such subspace is of dimension 2 to the k because your code space is of dimension 2 to the k. And you need to pack these many subspaces of dimension 2 to the k within 2 to the n if you want to be able to detect all of them unambiguously. There should be no scope for overlap between any two of these subspaces. And so all of this should be within the 2 to the n dimensional space. So this is the Hamming bound. So the question was, if, so suppose we are only interested in encoding a single qubit, so k is equal to 1, and we are interested only in correcting single qubit errors, t is equal to 1. So what is d then? D is 3, as we just saw. What is the smallest n? And you can work this out, right? So if t is 1, then what you have on the left, and k is 1. So you have c of n comma 0 plus c of n comma 1 times 2, right? Should be less than or equal to 2 to the n. So which in turn implies 1 plus 3n times 2 should be less than or equal to 2 to the n. So this is what the quantum Hamming bound looks like, right? For single qubit errors, if you restrict your attention to only single qubit errors and encoding a single qubit worth of information, right? So what is the solution for this? What is the smallest solution for this? I hope you can see the smallest solution is 5. So this tells you that n is greater than or equal to 5, right? So the shortest general purpose quantum error correcting code is a 513 code. Okay. Note that there is no contradiction between saying this and still discussing the 3 qubit repetition codes, because these are not general purpose quantum codes. They are for specific noise models. And this is always possible, that if you're interested in correcting for a specific noise model, you might end up with being able to encode into fewer qubits, right? So today I would say that what people study is both kinds of codes. People study general purpose error correcting codes also because they seem to have more of an advantage. However, from a resource constraint point of view, because these kind of tailored, or noise adapted error correcting codes seem to have the advantage that they require fewer qubits. So having to implement an encoding circuit with only 3 qubits is much more easier than having to implement an encoding circuit with 5 qubits. And in fact, if you look at the 5 qubit code that exists today, and I will write down the 5 qubit code in some form, if not in today's class, then in Monday's class, you will see that the encoding circuit is highly complex, requires CNOT gates across different qubits, whereas the 3 qubit code, as you saw, had such a simple encoding and a simple decoding circuit, right? So tailoring a code to a noise seems to have certain advantages, but of course it does not have the charm or the advantage of having a general purpose code which is going to correct for any arbitrary quantum error, single qubit error, or how many ever qubits. Okay, so this was about code parameters and the Hamming bound again, because I did this in the very last minute yesterday. I just wanted to revisit this quickly. Any questions? Okay, so let's move on to now talking about the stabilizer idea. So this is a discussion you will find somewhat elaborately done in section 10.5 of Nielsen-Chuang. Note that the error correction conditions and all of that we've discussed, quantum Hamming bound, everything you can find in Nielsen-Chuang. There is one section of Nielsen-Chuang which I will not talk about, which comes before the stabilizer formalism, which has to do with classical error correction, okay, and which has to do with classical, what are called additive codes and so on. That is an interesting discussion, but I will not get into that because that kinds of takes us into the domain of classical coding theory, which not many of you may be familiar with. So I will not get into that. Rather, I will move on to talking about the stabilizer structure, because that is an important aspect of quantum information theory in general. And also this is how you will find most discussions on quantum error correction happening in the literature today. Okay. So first of all, what is the idea of a stabilizer? So the idea is to be able to describe states via operators that stabilize them. It's another way of saying operators that leave the states invariant. So the idea is to move away from talking about codes. So far, how did we describe the codes? We wrote down the code words. Now, in the case of Shure's 9-qubit code, the description was not so bad because it was just a tensor product. It had a somewhat of a tensor product structure, so I could write down the code words like this. But imagine writing out this superposition fully. Imagine writing out an entire superposition of these kind of 9-qubit basis states, right? So it seems to be a somewhat inelegant way to describe a quantum code, and indeed it turns out there's a much nicer way to describe quantum codes in terms of operators rather than states, and in particular in terms of Pauli operators, because those are the errors that we are interested in correcting anyway, right? So we are now very much within the domain of this general purpose error correction, and that's where the stabilizer formalism gives us a way to describe codes in terms of operators. So first, let's learn to describe states in terms of these stabilizer operators. So I'll give you a simple example of this idea. So consider the standard Bell state. I hope you all still recall what this is. This is this 2-qubit entangled state, right? Now, think about what happens to the state under the action of what I will call x1, x2. Remember, this is nothing but x on the first qubit tensor x on the second qubit, right? So this acting on this state yes gives me back the state, right? Similarly, Z1, Z2 gives me back the state. So this state is a +1 eigenstate of both x1, x2 and sorry. It turns out that you can show that in fact this is the only, so I shouldn't put this dash, let me just say +1 eigenstate. This is in fact the unique state. So it turns out that you can show, and maybe I'll leave it for you to verify this, that this is the unique 2-qubit state that is left invariant under the action of both these operators, x1, x2 and z1, z2. And left invariant means it's a +1 eigenstate of the operator, right? That's what it means. If I say that an operator S acts on a state and it leaves the state invariant, it means that the state must be a +1 eigenstate of that operator. So those are synonymous statements. To say that the state is left invariant under the action of an operator is the same as saying that the state is a +1 eigenstate of that operator. So what is one saying? One is saying that this Bell state is a unique common eigenstate of x1, x2 and z1, z2. So first of all, let us note that x1, x2 commutes with z1, z2. Is that right? Yes, because x1 does not commute with z1. x2 does not commute with z2. But the tensor product of two Paulis, x tensor x commutes with z tensor z. You worked out such problems in your mid-sem and end-sem last semester, I think. So because they commute, they do admit common eigenstates. And their common eigenstates, remember these are Paulis, right? So they are either going to have +1 or -1 eigenstates. So this is the unique common +1 eigenstate of x1, x2 and z1, z2. So we say that the state beta 0, 0 is stabilized by x1, x2, z1, z2. So this is the idea of associating operators with a state via the fact that this is a state that is left invariant under the action of a certain set of operators. So this statement, in a sense, uniquely identifies this state because it says that if I want to talk about what are the states that are stabilized by this pair of operators, then I end up with beta 0, 0, right? So you note that it has to have the 0, 0, 1, 1 structure if it has to be stabilized by x1, x2, because x1, x2 is going to flip the bit, right? So it has to have this permutation symmetry. So you could jolly well also have 0, 1, 1, 0, for example. That's also a +1 eigenstate of x1, x2. However, 0, 1, 1, 0 will not be stabilized by z1, z2 because that will bring with it a minus sign. So if I look at the 4 Bell states, for example, then you can see that this is the only state which is stabilized, which means it's a +1 eigenstate of both x1, x2, and z1, z2. So taking commuting Pauli operators and trying to associate states that are left invariant by them automatically imposes a certain structure on those states. And that's what the stabilizer formalism does for us, right? Okay, so now, like I said, I want to, instead of talking about the code words associated with a state, I want to talk about a set of operators that will leave the code words invariant. So we did this exercise for a single state. Let us now do this exercise for the 3-qubit repetition code. So I will introduce the stabilizer formalism again via an example, namely the 3-qubit bit flip code. So remember that the code space is the vector space that is spanned by the 0L and the 1L, right? Where 0L was 000 and 1L was 111, right? So now I can go back and ask, can I identify a set of commuting Pauli operators that stabilizes this code space? So this assumes already that if a particular state, or rather if two states are stabilized by some set of operators, then a linear combination of those states also stabilizes the operators. Okay? So in some sense, this is assuming that there exists a vector space structure, right? So let's first see if that is true. So suppose states psi1 and psi2 are stabilized by some operator. Let me call this A, right? Then what that means is A psi1 is psi1, A psi2 is psi2. So A acting on alpha psi1 plus beta psi2 is also alpha psi1 plus beta psi2. So you see the vector space structure naturally emerges when you talk about the stabilizing action, right? So this should automatically become clear to you if you have done your linear algebra courses seriously enough. Because what is this saying? This is saying that it is simply saying that I have two states that are +1 eigenstates of A. So obviously, a linear combination is also a +1 eigenstate. So naturally, when you talk about the +1 eigenspace, so what is one talking about when you're talking about a space that is stabilized by an operator? So the vector space stabilized by an operator A is nothing but the +1 eigenspace of the operator A, right? So first of all, these are, if you have to have more than one state that is stabilized by the operator, there must be degeneracy, right? This must be an operator which has more than one +1 eigenstate, right? Because you're talking about two unique states, huh? Right? You're talking about two unique states that are stabilized by the operator. So it must mean that there is degeneracy. And when you have degeneracy, then with every eigenstate, you associate not just a single eigenvector, but you actually associate an entire eigenspace. And the +1 eigenspace of an operator is what will be the vector space that is stabilized by the operator, right? So that now brings us back to the question. So I have convinced you that if I have more than one state that is stabilized by one operator, then there must be an entire vector space that is associated with that is left invariant by that operator, right? Now you're going one step ahead. You're saying that consider some set of commuting Pauli operators, not just one operator, but some set of operators, right? So this is the first point, that there is a natural vector space structure. The second point is, if you have to talk about stabilizing a vector space, then you need to talk about commuting Pauli operators, right? So suppose I talk about the stabilizer. So let me talk about stabilizer associated with a code space C. Then this stabilizer must be a set of commuting Pauli operators So this stabilizer is what I call S, right? But it is more than a set, right? If I consider a set of Pauli operators, then they naturally form a more interesting structure than a set. What is the structure? They actually form a group. So it's actually a group under multiplication. Okay, so why is that? So let's now therefore jump ahead and start talking about the Pauli group. So I'll first talk about the single qubit Pauli group, right? So let me first talk about the single qubit case. So and I'll call this P1, okay? So consider the set of all Pauli operators on single qubits. What is this set? And now I'm going to put some prefactors also. There's plus minus identity, plus minus I times identity, plus minus x, plus minus I times x, plus minus y, plus minus I times y, plus minus z, plus minus I times z, right? So this is the single qubit Pauli group, and it is a group because it is closed under multiplication. It is associative. It has an identity element, which is nothing but your I itself, right? And it has inverse. Every element has an inverse. So this forms a group under multiplication, that is standard matrix multiplication, but it is not a commutative group. It is not an abelian group. It is a non-abelian group. Non-abelian simply means that not all elements commute, right? So now we can extend this idea and talk about Pauli groups on multiple qubits, right? Pauli's on multiple qubits and the associated Pauli group, because the same properties will carry over. You just have to remember how we wrote down the set of measurements you have to do, for example, in the case of the Shor code or the 3-qubit bit flip code, or when we write down the set of errors, etc., they're all tensor products of Pauli's, right? So we can talk about more generally the Pauli group on n qubits, right? So, and that will be our focus. So you can talk about the Pauli group on n qubits. Well, it is simply tensor products of this form, right? Where you have identity tensor something. So let me just write it like this. So you could have, so let me denote it as Pn, right? Which is simply sets of operators like this, where you have x1 to the, let me call it R1, z1 to the R1, tensor x2 to the R2, z2 to the R2, tensor, etc., xn to the Rn, zn to the Rn. What do I mean by this? What is R1 and R2? Oops, sorry. I want to say S, R and S, sorry. R1, S1, R2, S2, Rn, Sn. Okay. So each Ri and Si can be either 0 or 1, right? And I hope you see that this is a way of writing down a general n-qubit Pauli operator. Yes? I'm putting the subscript just to indicate that, which qubit one is talking about. So on the first qubit, if both of them are 0, then it's identity. If one of them is 1, then it's either X or Z. And if both of them are 1, then it is Y. What I'm missing out here is all the prefactors. Now, why did I have to put all these prefactors here? The plus minus 1 and the plus minus I? Because if I didn't put the prefactors, this would not be closed under multiplication. This would not satisfy the group property, right? So if I'm listing out the elements of the group, then I better also include the phase terms here. So I also have to include the plus minus 1 and the plus minus identity. Okay, so it's understood that there could be a plus minus 1 or a plus minus identity in front. And then you have all possible n-fold tensor products with just identity at any location or x, y, z in some form, right? So this Ri and Si, so essentially what you have, like these two binary strings which are parametrizing these n-qubit Pauli operators, right? So this is for all I going from 1 to n. Okay, so this is the Pauli group on n qubits. This is also not a commutative group. It is also a non-abelian group. So now let me formally define what a stabilizer is, right? So having defined the n-qubit Pauli, let me formally define a stabilizer. Given a code space C, which is some subspace of the n-qubit space, right? Doesn't matter what the size is. So you're talking about, so for example, this could be, if it's an NKD code, it will be a 2 to the K dimensional subspace of the 2 to the N dimensional subspace, right? So given some code space C, consider the set of all, consider the set S. So I will say S associated with C, right? Which is the set of all operators S which belong to the n-qubit Pauli group such that they leave every state in the code space invariant. S is called the stabilizer or the stabilizer group Okay, maybe I still have to show that it's a group, but that'll become clear very soon. Associated with the code C. Okay. So consider the set of all n-qubit Pauli operators which leave every state in the code space invariant. Right? So this set is what is called the stabilizer associated with the code, and we will see that this will indeed form a group. Not only will it will form not any kind of group, it will actually form an abelian group, right? So why is that? So suppose I want to say that, okay, so let us look at the 3-qubit code example, and then maybe now things will become a bit more clear. Oops. So the 3-qubit code, oops. So let us go back to the example, 3-qubit code. Code space is span of 0, 0, 0 and 1, 1, 1. So now you will tell me which are the set of Pauli operators that leave this code space invariant. So what is n in this case? N is 3. So we are looking at the 3-qubit Pauli group. P3. So which are the operators, the tensor products of Pauli's, etc., which leave these states invariant? Remember, it has to leave both the states invariant, and that is when it is going to leave the entire code space invariant, right? That is when it will leave any state in the code space invariant. So which are these operators? So first of all, you will note that you cannot have, so I want to now construct this set S of Pauli operators, which are going to leave both these states invariant. If I find operator that leaves both the states invariant, that's going to leave any complex linear combination of that also invariant, right? So of course, identity. So let me say identity tensor 3. That's an element, right, of this stabilizer set. Let me call it a set for now. Can I have an X operator? Can there be an X operator in this set? X1, X1, X2, X3, anything?
No.
Yeah, so you can only have Z. Okay, good. Single Z?
No.
It has to be pairwise Z. So Z1, Z2, for example. Yes. Z2, Z3. Oops. And Z1, Z3. So what I'm saying is the operator ZZI, IZZ, ZIZ, right? And you will see that that's it, right? Because I cannot have X. So if I cannot have X, then there's no question of there being Y anywhere, right? So that's it. So from the set of all 3-qubit Pauli operators, I have identified a set of 4 operators which leave both 0, 0, 0 and 1, 1, 1 invariant. And you will notice, of course, that the elements of S all commute, right? And S actually is closed under multiplication. Now this is easy to see. Suppose I have 2 operators which stabilize a state. Let me say P stabilizes the state psi. So This is to tell you that there is always a group property here. And if I say that Q stabilizes psi, then if I consider the product PQ, then obviously that is also something that is going to stabilize psi. So if P and Q belong to the stabilizer set associated with a particular state, the product PQ must also belong to that set, right? So I hope it's clear that whenever one talks about more than one operator, so just like how if you talk about more than one state being stabilized by an operator, then there is a vector space structure. Similarly, if you talk about more than one operator that leaves a state invariant, then there is a group structure. So it is not just that set of two operators, it is a group formed by those two operators, right? So here you have a group of Pauli operators, a group of 3-qubit Pauli operators. So S is a commuting, and the fancy way of saying that is abelian. And of course, it's a subgroup, right? It's a subgroup of the larger 3-qubit Pauli group. So S is a commuting or abelian subgroup of P3. And you can see that if I multiply identity with any of them, I get back the same thing. If I multiply these two, I get the third one, right? So in fact, I can then even talk about generators of the group. I can talk about the group simply being generated by two of these Pauli operators, Z1, Z2, Z2, Z3, and that's it. So is this idea clear of associating a stabilizer group, a group of Pauli operators that leave the entire code space invariant, right? Questions?
Ma'am, is there any mathematical notion of calculating these stabilizers from this code space, or we just need to use our intuition to get these operators?
Yeah, that's a good question. So it actually works the other way around, right? So it is often easier to construct commuting subgroups of Pauli operators, okay? And then try to identify what is the vector space that is stabilized by this set of operators, right? But if you have states already, then identifying the operators is usually a harder problem.
Yeah.
Right? Well, there is still a way of doing it by constructing different projectors. It's basically like saying you have the +1 eigenstates, right? So using that, you have to go back and construct the operators, right? So you can, in a way, do it by taking the projector onto the +1 space and trying to do, but it's actually, yeah, it's a much harder problem. The easier problem is to actually go, given a set of, commuting operators, it's easy for you to identify what is the +1 eigenspace, common eigenspace of those operators, right? And so that is why the stabilizer formalism is interesting, because it gives you a way to construct quantum codes without having to laboriously look through multi-qubit states and trying to identify a subspace there. You rather just look at Pauli's, you try to form commuting groups of Pauli's and then look for their eigenspaces, right?
Yes, no.
Yeah. Okay. So let us now try to formalize this a bit more. So this was just the simple 3-qubit example. So by the way, one last point. Do you notice something about the operators in the stabilizer group? The Z1, Z2, forget the identity. That's I hope you now realize that the stabilizer group will always have, so let me note this also. And identity, so let me note down, let's say, some properties of this. So first of all, it's a commuting elements of these commute. Second is that it forms a group. So oops, it's closed under multiplication. And the third thing you can observe is that identity is always an element of S. And that also comes adds to the group property and all of that, because identity will always stabilize any vector space, right? So it's always an element of the group. So that's why it's a valid subgroup, because it always has the identity element. And because of the property of the Pauli's that they all square to identity, you always have the inverse element also. Okay. Yeah. So do you notice something about these Z1, Z2, Z2, Z3, Z1, Z3? If you go back to how we detected errors for the 3-qubit code, does it ring a bell? What were the measurements that we did in order to detect errors on the 3-qubit code?
Parity check of two nearby qubits.
Correct. So what was that parity check actually?
Yeah, if
Z measurement.
It was indeed a Z measurement. Exactly. So if you notice what the elements in the stabilizer are, these were in fact the operators that we were measuring in order to detect the errors. Okay, and that's the reason again why this formalism is important. So note that so let me call this as S3. Okay, so because I just want to associate this with a particular code, it's a 3-qubit repetition code. So S3 has identity. So when I write identity, it's understood it's a 3-qubit identity. Okay, Z1, Z2, Z2, Z3, Z1, Z3. So these are the measurements that are used to detect the X errors. So in a sense, what we were doing with the syndrome measurement was actually measuring the stabilizers associated with the state, or rather associated with the code. Okay. Also note, so this is note 1. Also note that I don't need to list out all the operators. I can simply talk about the generators of S3. So I hope all of you are familiar with a little bit of group theory, at least, where you know what generators are, right? What are generators of a group? They are elements from which you can generate the entire group via multiplication, right? And what are these generators? Any two of them, right? Z1, Z2, Z2, Z3. And in fact, these were the very operators that we were measuring. If you remember the circuits, it looked like this, right? I was looking at Z1, Z2, and then this was Z2, Z3, right? And I was measuring this here. So in fact, these stabilizer generators were exactly what were being measured if you recall the error detection circuit. Okay. So the rest of the elements of S3 are simply generated by multiplying these two generators. So the generators are basically a set of independent operators from which you can generate the entire group, right? Okay. So just a bit more general stabilizer theory, and then in Monday's class, what we will do is to look at the error correction conditions in terms of stabilizers. Okay, so I've already listed out the properties that the elements must commute, identity must be an element. So let me maybe add something to that. So let me add a few more properties now. I just noted a few based on this example. So let me note down a few more properties. So those were maybe the more trivial properties. We'll note down slightly non-trivial properties now.
Syndrome measurement being equal to measuring the stabilizer.
Sorry, can you say that again? I only heard half your question.
I'm saying, is this the general feature of all other stabilizers? This syndrome measurement being equivalent
Yes,
to
yes,
measuring
yes. Indeed, it will be. It will be when we'll discuss the error correction properties, and I don't want to do that today because that will start off. That's a longer discussion. So indeed, it will turn out exactly to be this case. This equivalence which we have noted here is going to hold beyond just the 3-qubit code. See, the idea is this, right? You have identified some set of operators which leave the code space invariant. The information that you want to protect is sitting inside the code space. What do the errors do? They corrupt this information. So they take you outside the code space. How do you detect this? Well, you measure those very operators which left the code space invariant. Now, because these are all Pauli operators and your errors are also of the Pauli type, things either commute or anti-commute. And when they anti-commute, you can detect that change that happens to your states via measuring those operators. So this is the sort of rough hand wavy argument to tell you that this equivalence actually is at the heart of the stabilizer formalism, that once you identify a code using its stabilizers, you're done. So I needn't have gone through all that discussion with the single qubit, with the 3-qubit repetition code, showing you how it maps different X errors here, there, etc. Then do the syndrome recovery. All of that is encapsulated here. This identifies the code for me uniquely. This identifies immediately what is the measurement that I need to do in order to detect the errors. In fact, it even identifies what is the set of errors that are going to be corrected by such a code. Okay, and that's what we'll do on Monday, where we'll discuss, given the stabilizers, how do you identify the errors that can be corrected by that code? Just like how given the projector on the code, we wrote down the error correction conditions, you can now do the same thing, but in a more elegant and sophisticated way using the stabilizers. Okay, so I just want to finish by noting a couple of more properties associated with the stabilizers. So I think I noted 3 properties. Because 3 identity belongs to S. Yeah. So just as I said, identity belongs to S, I hope you realize that minus identity cannot belong to S. Okay. Because if there is a particular state that is going to be stabilized by minus identity, what does it mean? Yes. It means that the state itself is the null vector, right? So I cannot have any state that is stabilized by minus identity. So minus identity is not an element of the stabilizer, just like how we said plus identity is always an element of the stabilizer. And the last thing that I want to note is the size of the stabilizer. So remember this generator property, right? So let me just quickly recall the idea of generator and then talk about the size of the stabilizer. So recall that if you have a group G with generators G1, G2, etc., let me say GL, right? Then every element of the group G can be realized as some power of each of these multiplied together, right? So G1 raised to AM, A1, G2 raised to A2, etc., GL raised to AL, right? Some product of these elements probably raised to multiple powers, right? And I already showed you for the 3-qubit code how you just need those two operators, Z1, Z2, Z2, Z3, or any two of them, right? For that matter, that can constitute the generators of this group, right? So now, if a stabilizer group has R generators, so if a stabilizer has R generators, so what I mean is I have some stabilizer group associated with the code space C. So note that when I write down these angle brackets, that denotes generators, right? That's standard group theory notation. So I have some R operators that generate this. Then any element S of the stabilizer can be written as, M1 raised to R1, M2 raised to R2, etc. MR raised to, yeah, let me stick to the A notation. So, sorry. Yeah. So the question is, how many elements does the stabilizer group have? Right? So if a stabilizer group S, this is this capital or bold S, has R generators, then any element can be realized like this. So what is the cardinality of the group, or what is the size of the group? Yes? How many elements does the stabilizer group have? Is it so hard? Remember, these are all Paulis, right? And what can you have? You can have each of these A1, A2 to AR can be either 0 or 1, right? So, yes. So each AI is either 0 or 1, right? So I have basically R bit strings, binary strings of length R. So how many of them do I have? 2 to the R. So a stabilizer group, remember these are subgroups of Pauli groups, right? So these are all Pauli operators. So the stabilizer group has R elements, sorry, is generated by R operators. Then it has a total of 2 to the R elements, right? And R, of course, is smaller than or equal to N because we are talking about N qubit operators. So yeah, so this is the connection between how many generators you can have and how many elements in the stabilizer group. Again, you can revisit this example that we did of the 3-qubit code. Remember that this is the group generated by two operators, Z1, Z2, Z2, Z3. So the total group itself had 4 elements, right? It had identity tensor 3, Z1, Z2, Z2, Z3, and Z1, Z3. Okay. So R is 2 and the cardinality of the group is 4. Okay, let me stop here. And on Monday, we will take this further, take this discussion on stabilizers further and ask can we now identify the error correcting properties of a code based on its stabilizers? Okay. Questions? Okay, there are no questions, then I'll see you on Monday. Okay.